So now what we're going to try to take a look at is really a little bit more of how the gases move the direction they do. So now we've talked about how to get the air into the lungs, and this is about why the particular gases travel the direction they do. The thing I want to say right off the bat is, in reality, this is simple diffusion. We have to talk a little bit about some things that influence it, but in reality, it is simple diffusion. It's going from highest concentration to lowest concentration. When we're trying to explain how these gases are going to move and how much they're going to move, what we really get into is we start talking about what is called partial pressure. This really has to do with the fact that we've kind of said atmospheric pressure is 760 millimeters of mercury. But when we're talking about the air, we're not talking about a gas that is 100% oxygen. It is a combination of gases. And what we're going to see is each one of those gases, based on the percentage, makes up that particular part of atmospheric pressure, which is where we get this idea of a partial pressure. So we have like the partial pressure of oxygen is going to be 760, and oxygen is about 21% of the atmosphere. So it's that 760 times 0.21 to get you what the oxygen's partial pressure is in the air. Nitrogen's close to 80%. That's kind of getting you what its pressure is. So how we measure these is in millimeters of mercury. And how we rate them is P, partial pressure of O2. So big P, O2. Again, each gas is going to move with that particular partial pressure gradient. If it's higher in the alveoli than it is in the blood, it's going to enter into the blood. If it's higher in the blood than it is in the alveoli, it's going to enter into the alveoli. So all the gases in the environment combine to make this atmospheric pressure. So things like nitrogen, oxygen, a little bit of carbon dioxide, water vapor, other gases that are there, all those that go together to make that 760. And each gas, its partial pressure is its percentage times that 760 or whatever, depending on the altitude that you're at, whatever atmospheric pressure happens to be at the altitude that you're at. So for example, like I was saying, nitrogen is just under 80, so it's 78.6% of the gases in the air. So the partial pressure of nitrogen is that 760 times that 78%, which ends up being 597 millimeters of mercury. Again, I'm not going to ask you the specific numbers of the millimeters of mercury, but you need to understand what a partial pressure is and how it's going to influence which way the gases are moving, as we'll see in just a minute here. If we add up all the partial pressures of all the separate gases, it will be equal to that atmospheric pressure. So, and again, that law here with these partial pressures in Dalton's law is that overall atmospheric pressure is the combination of all those gases. So each gas has its own partial pressure. Atmospheric pressure is going to be a combination of all those partial pressures. What we're going to see is, depending on what we're doing with these gases, partial pressures in one region of the respiratory system can be higher than another. And again, simple diffusion, higher concentration to lower concentration, or higher partial pressure to lower partial pressure. So for example, you bring oxygen-rich air into your lungs, into the alveoli, it's going to have a higher partial pressure in the alveoli than it is in the blood. So it was going to travel down that to try to equalize those partial pressures. So we're going to see gas exchange at the alveoli, gas exchange at the tissues are going to be dependent upon these gradients, which again are just, in reality, simple diffusion, but we're using the words partial pressure instead of concentration. But the same idea. One of the things that is interesting with the body is the partial pressures in the alveoli are not going to be what atmospheric is. And this just has to do with the fact that, again, we have dead airspace in our lungs that is not exchanging gases. And the other thing is we do not empty out our lungs. So because of that, we can't bring in completely fresh atmospheric air. There's going to be some air that was staying in the lungs that is not getting exchanged with the atmosphere. The other thing is we're going to have oxygen and carbon dioxide moving in and out of those alveoli. And the final thing there is there's definitely going to be more water vapor. If you've ever been out on a cold day and you exhale, you can see the water vapor in your breath. It is definitely going to be higher than what's in the air. So within the alveoli, the atmospheric pressure, within the alveoli, the partial pressure of oxygen is higher. I mean, the partial pressure of oxygen is going to be lower than what is in the atmospheric levels here, carbon dioxide is also going to be much higher than what it would be in the atmosphere. So when we get to our systemic cells, oxygen tends to be much lower partial pressure, carbon dioxide much higher partial pressures. So when we're moving these things back and forth in the blood, it's going to change as it goes through different capillary beds and drops off and picks stuff up. In the alveoli and the systemic cells, it's kind of staying pretty constant. We're completely replacing that air usually. These numbers are going to stay pretty consistent. The thing that's interesting about this as well is that atmospheric pressure can change based on altitude. If you go to, everything we've talked about so far is based on that sea level of 760 millimeters of mercury, which would make it about 597 of nitrogen, about 160 millimeters of mercury in the atmosphere. You can see in the alveoli it's going to be less because we can't completely exchange those gases. The other thing you see is CO2 in the atmosphere is quite low, 0.04%. Very, very small. As we increase in altitude, what we're going to see is if you go further up, there's less atmosphere above you. There's less atmosphere above you, there's less pressure it can exert. And even though the gases are going to be consistently the same in that, in terms of percentages, if we go up to 10,000 feet, atmospheric pressure is only 523 millimeters of mercury, which means 21% of that is only 110. And then if we figure out what's in the alveoli, it's only about 67 millimeters of mercury. So just going up 10,000 feet, the partial pressure of oxygen in your alveoli is going to drop by 1/3. As you can see, you go up to 20,000 feet, it's well under half of the amount of oxygen getting to your alveoli as you go up. They talk about really at about 26,000 feet is considered the death zone when you start talking about mountaineering and other stuff like that. Above about 26,000 feet, there is not enough oxygen to sustain life long term, which is part of the reason if somebody is climbing Everest and they get up there for too long, we can get some interesting things happening there where they're not going to survive because over time they're in the process of dying because there's not enough oxygen, and it's just whether or not they get back down in time. They might be able to survive a day or so above that level, but long term it will not sustain life. And you can see as you start getting up, up 30,000, 40,000 feet where airliners are kind of flying, you can see if we didn't pressurize the cabin, there would not be near enough oxygen to sustain life. And that's part of the reason if there's ever a decompression on a airplane, they're going to get it down to these probably under 10,000 feet rather quickly. Another thing that's interesting with this is if you're using pressurized gases and breathing underwater, for about each 10 meters you go down, you're actually going to get a doubling of the atmospheric pressure. So it's kind of shown there. If you go down to about 33 feet, what's going to happen is atmospheric pressure is going to be about double normal. What that means is all those gases are going to be twice as much partial pressure in there. Again, usually not an issue. To get these to stay in solution and go into solution, you have to have that regulator giving you it at the particular pressure that you're at, because you also have that water pressure pushing on the outside of you. So you need more pressure to push out against that. This is part of the reason if you go down a little bit lower, if you get down to like 3 atmospheres, if you come up too fast, if you've ever heard of the bends, what's going on with that one is nitrogen is normally not an issue in the blood. But if you start going down to 3 atmospheres plus, what you're doing is you're getting a lot of that nitrogen into solution in the bloodstream. If you all of a sudden take all that pressure off, it's kind of the similar idea of taking a soda bottle, shaking it up, and then taking the lid off. All that gas was being held in solution by the pressure against it. If you all of a sudden relieve that pressure by coming to the surface, all that gas trapped in the solution is going to come out of solution. Same thing would happen if you were in space in a spacesuit and then you lost the spacesuit there. You're going to have those gases coming out of solution. You actually can get the bends in space from the same thing. The other thing that's kind of interesting that plays a role in this is the final gas law that we have to talk about, which is Henry's law, which kind of says that how the gas is going to move and how it's going to go into liquid is dependent upon its partial pressure, which we've been talking about already, but also how soluble that gas is in the particular liquid. Again, partial pressure is going to be the force driving stuff in there. The main thing is what we're going to see is carbon dioxide can dissolve in water a little bit easier. It's a little bit more soluble. Oxygen is not. So we can't put a lot of oxygen into a liquid solution, which is part of the reason we carry oxygen by hemoglobin and not just dissolved in the plasma in the water. But as you can get the example, you can get a decent amount into soda by doing that. But if you really want to get highly carbonated beverages, you actually force CO2 in there and then seal it. And again, any gas, any liquid given the time with an atmosphere is going to try to reach its equilibrium with that particular atmosphere. So if the partial pressure, and this is the reason soda goes flat. If you have a soda sitting on the counter and you take the lid off, there's way more higher partial pressure of CO2 in the water than there is in the air. So what's going to happen is over time, that CO2 is going to leave the liquid and go into the air, which is part of the reason every time you seal it back up, if you let it sit for a while, you take the lid off, it will, because it's pressurized to that particular size container. And then when you open it up, it relieves that pressure again. And that's why over time, soft drinks will just go flat if you open them, close them enough times, and you pour a little bit off. And again, variability in the solubility of this is definitely the case. Carbon dioxide, much more soluble than oxygen in liquid, in water. Nitrogen, not very much at all, about half as soluble as oxygen. So we're going to kind of see that's part of the reason if you breathe those pressurized gases, that nitrogen can come out of solution really easily if you remove the pressure. But again, constant interaction between whatever the liquid and the air means it's always going to try to reach an equilibrium. And again, what this really means is you need quite a large gradient to order to push something in there that's not particularly soluble. And again, that's why normally at atmospheric pressure, we don't get a lot of nitrogen in the blood, and it's not an issue. But during diving, because we're upping those partial pressure gradients so high, so we're doing 3-4 times atmospheric levels of nitrogen, you're going to push a lot of nitrogen into the blood. And if you all of a sudden remove that pressure, that's why it can get gas out in the bloodstream and give you the bends. And that's what decompression sickness is. It's like if you're down there, you get a lot of nitrogen forced into the blood. If all of a sudden you remove that pressure that's holding it in solution, kind of like a soda bottle and having the lid on it, holding that gas in solution, you drop a soda bottle with the lid on, it doesn't all of a sudden go, but if you take that lid off, it'll all come out of solution. It's kind of the similar idea with nitrogen in the blood. The thing that's neat about this is if you actually, the amount of time it takes to decompress, the deeper you go, the longer it takes. But once you get down to it being compressed, you can stay down there more and pretty consistent for a period of time. So what they do, sometimes like people that are doing deep sea diving on like oil platforms and that, they actually have a pressure chamber that they will bring it down to them where they're underwater, have them get into that one. They can bring it back up to the surface, but keep them under pressure so they don't have to do these long-term decompression, recompression things, and they can stay working a lot longer. So it's kind of neat that way. We can also use these higher pressure things like we were talking about before with carbon monoxide poisoning. Sometimes you can put people under more pressures and with higher levels of oxygen to try to force some oxygen into these areas. So when we really start looking at how the exchange happens, in the alveoli, it's about 104 millimeters of mercury. The partial pressure in the pulmonary capillaries of the blood that's coming there is about 40. So we can see higher partial pressure in the alveoli, lower in the capillaries. It's going to try to go across there and reach equilibrium where it will come decently close. So carbon dioxide, we're going to see kind of the opposite. In the alveoli, it's about 40 millimeters of mercury. It's slightly higher than that in the pulmonary capillaries. Because of that, it's going to leave the capillaries, go into the alveoli, and try to, again, reach equilibrium. So what we're going to see is just kind of this exchange of gases. As the blood comes back, we know it's high in CO2, low in oxygen. We know the alveoli, lower in CO2, higher in oxygen. With this partial pressure, CO2 is going to go out to the alveoli. O2 is going to come in. You can see they reach very close to equilibrium here. Travel through the bloodstream when it gets down to the tissues because the tissues are using oxygen and generating carbon dioxide. You can see oxygen has much higher partial pressure in the blood. It's going to leave the blood to try to get to the tissues where CO2 partial pressure is higher in the tissues than it is in the bloodstream. So it's going to leave to go in there. And then again, we see the opposite thing happen again based on what's going on in the alveoli. Again, a lot of this is dependent upon our surface area. So we have a lot of surface area in the alveoli. Again, diffusion distance. This is one of the things that is an issue with the COVID-19. It gives you a pneumonia. If you get fluids in your lungs, it increases that diffusion distance, which decreases the ability to get oxygen in. And again, pressure gradients, higher altitude, you have a lower pressure gradient, it's harder to get more into the blood. And again, one of the other things you do is by breathing faster, breathing deeper, we can exchange more fully those gases in there and maybe get this more to like 35 and this a little bit higher by breathing faster and deeper like that. And this just, I kind of already said this one here, talking about the internal respiration down at the other end here. One of the things that's interesting is only about 25% of the oxygen that's in the blood actually enters the cells, which is part of the reason with CPR and that they say if you can keep the heart beating, you don't necessarily need to do the breaths for a period of time because there's actually enough oxygen to keep those cells alive as long as you're getting that oxygen moved around so it's getting to those areas. Again, oxygen doesn't dissolve well in the plasma because it's not very soluble. Because of that, we carry it on hemoglobin. So about 99% of our oxygen is carried on hemoglobin and only about 1 to 1.5% is carried in the plasma. We're going to see CO2 being much more soluble. 7% dissolves in the plasma. Some of it's carried on hemoglobin and a lot of it is carried as in a buffering thing called bicarbonate. So, and that's one of the things we'll be talking about the next time here is how do we carry these gases. Next show is actually hemoglobin dissociation curves, and then, like I said, a little bit about how we carry those respiratory gases. So I will see you next time.